you very much, John. Today I talk about some metaphorical model of biological evolution based on the concept of evolution through maps. So I see here this picture was drawn by Escher, very famous, which I found most interesting in the present context of my talk. So in the following two aspects. The first aspect is that the pattern itself evolves. Okay. So you can see the clear transitions from one pattern to another patterns through the intermediate vague, rather vague or chaotic regions. And the second aspect is that the evolution of the pattern itself, which could be supposed to occur in time, is embedded in space here. So these aspects gave me a strong motivation for the present study. So I've been engaged in the brain sciences for these 25 years. But on the other hand, I've been involved in the evolution study only recently, just a few years. So whenever I consider anything about the biological evolutions, I've been used to consider the corresponding concept in the brain. So for instance, for gene and synapse, the genotype synaptic states, for phenotype the neural states, for selection threshold, the selection of metric, or the selection of some variation of principle. For landscape, the neural manifold, the selection rules correspond to run rules. The individual is selected, on the other hand, the brain is run. The mutation, the synaptic and the nucleus, for instance. But this correspondence itself is problematic, but today I'd like to take this double standard in my talk. So I'll talk about two topics which may be related to each other, I hope. The first one is the evolution by copy and identify process. So here now you see the X variable may represent some biological systems. N is a discrete time step, and it copied, and which is denoted by X prime, and fed back to the original system via the interaction, the nonlinear interaction. So this is an identified process. So the coupling strength could be the variable, not parameter here, but which is supposed to slowly vary in variable and much slower than the system's variable X. So additionally, I suppose the external supply and the natural decay of the system itself. So the equation of motions is something like this. So X variable decays by itself, but it's sometimes enhanced or sometimes depressed by the interaction terms depending on the sign of the Y variables or the interrelationship between the Y and X and X prime and external supply here. And the coupling strength itself changing, and it increased by the system parameter itself, but it changing further by the interaction term. But the sign is opposite. Okay, so this is very important. And Y could be minus as well as positive. So here we assume X prime will equal X. So that's the complete copy process. So this may represent the function of the mirror neuron or in monkey or mirror neuron system in human. But more interestingly, this equation of motion is just this discretized version of the translator. So original translator was invented by Prigozhin, Nicolis, and Lefebvre, and others in 1970s, early 1970s. in order to capture the essential dynamical behaviors in the Veloso-Jaczynski reaction systems. But actually not, the details of the dynamics of the Veloso-Jaczynski reaction system is much more complex than those that this equation of motion shows. But this equation of motion captures the essence of the dynamical systems. So behind in the non-equilibrium chemical reaction systems. For instance, it describes the appearance of the limit cycle oscillations. Okay, so discretized one. So this is almost the same equation of motions as I mentioned before, the copy and identify process. So, regarding the variable y as a parameter, we obtain a one-dimensional map, so-called logistic map, so which shows many bifurcation structures, including chaos and any period of periodic orbits. And here, so the y, if y is parameter, it represents the logistic map. But here the y changing slowly, much slower than the x variable. So what happens? So in such a case, so this map can be viewed as a random logistic map or parameterized logistic map. And we can also prove that the difference of y variable between the present and the next time step is the same order of the discretization step. And the series is a strictly monotone increase in the neighborhood of the bifurcation. So as a result, so you see, so here the right figure shows just one orbit starting from the initial condition around here. So the dynamical orbit experiences a very, very chaotic motions, but slowly changing in y variable, and it experienced bifurcations, many bifurcations it experienced, and finally the dynamical orbit come to the periodic regions and experience the inverse bifurcation, the period Darwin bifurcation, and finally it approaches to the fixed point. So which correspond to just equivalent to the steady state of the original cluster. But here the left figure shows the bifurcation diagram of logistic map. So as you see here, the trajectories of one orbit resembles very much the bifurcation diagrams of logistic map. So, okay, the second topic is about the evolution of mathematical functions, which may be related to the first one. So the motivation is that how could the neuron be evolved? So this work is ongoing. The model and simulation was done by Hiroshi Watanabe here, stand up. So he. And Takao Ito, he. So these two guys, my students. And he was so active to make this model. And we prepared varieties of functions, so by using this type of equation of the function. So this function contains the 6 parameters, gamma, alpha, omega, j. And by changing these parameters, the combination of these parameters, we obtain the constant functions, monotonous functions, including sigmoid functions, the unimodal function, the bimodal functions. So that's this functional form can describe as some subset of polynomial. So after some appropriate selection algorithm, so we adopt some very usually used genetic algorithm. So not so strange. The threshold function, that's a step function, was selected among the wide classes of functions. So therefore, by this mechanism, the excitable system is generated. So the selection pressure we adopted here is a maximum transmission of mutual information between input and each elementary network. So we prepared the coupled systems in one dimension, and we use the input. Okay, we feed the input. Okay, so that we can calculate the mutual information between the input and each element of the systems. So the variational principle is that we take the maximum transmission of mutual information. Then finally the step function, so which may represent the neuron. So we obtain the formal neuron here. Some more details. In the case of chaotic inputs, if the coupling constant is very large, the selected function goes to 0. So nothing happens. So no information is transmitted. But in the case of intermediate coupling constant, the step function is selected finally, by which the pulse train are propagated. So it is very plausible to describe the evolution of the neuron systems. And in the case of small coupling constant, again the step function is selected, by which the oscillatory behavior is propagated. I hope so. This stage is also represents some characteristics of the evolutionary process. And if we add some noise to this system, the step function, there is a tendency that the step function is more selective. And in the case of periodic inputs, there are much variety of selective periodic functions, which is synchronized with input, but it's independent of coupling constant. So let me summarize my first talk. So I gave you two topics, but which may be related to each other behind. And so first one is a discretized dynamical systems. The discretized dynamical evolution shows some similarity to the natural selection process. So, and as you see so in this picture, so for the first time, there's much variety of the species, for instance, as from that, so many varieties of species, only one species selected. So this is as an inverse, opposite process of the diversity, but it could be viewed as a selection process, or from many states to one state is selected, or anything about it. And the presence of discrete time is memory. So in this case, the memory is it's a very complex bifurcation structure. It's embedded, so this is a kind of memory. And the last topic, the second topic, is that a mathematical neuron, which can be represented by a threshold of step function, evolves under the restriction of maximum transmission of information. So at the moment, so we are now trying to study what happens, what the new functions could be selected by the different restrictions.